Okay, so hi everyone. Let me start sharing my screen. Okay, let me know. Is it showing up?
Yep, perfect.
Okay, great. So hi everyone. Welcome back. Thanks for joining me again. So this is going to be our second lecture on simps, and actually what we're going to delve into today are cannibals and elders. And then we're going to discuss dark sectors that give manifestations of all of these ideas and more. And so just to recap where we reached at the end of yesterday's lesson together, we've really worked out sort of the parametrics and the understanding of what happens for simps. And importantly, we now understand that there are actually two separate processes, or sort of two different knobs, that are important and required to happen for the simp miracle to work. So on the one hand, we have the 3 to 2 self-annihilations of dark matter. I remind you, I'm going to call dark matter is going to be chi throughout our lessons together. So this is the process that is setting the relic abundance of dark matter. And we also know that there's another process that has to be active in order for the story that we told to be consistent. And that is that at the time that freeze out is happening, we have to also have some way to shed heat or to dump entropy. And so, for instance, we have to have scattering of dark matter off of some standard model particle or some light bath particle. Okay, so these are the two processes that we have. This first one is the one that sets the relic abundance. Okay, and I remind you that we arrived at something that told us that the dark matter mass was roughly the self-coupling times around 100 MeV. So this is why we called it a strongly interacting massive particle. And this second process, which we described at the very end of our time together yesterday, is the thermalization process. And so this is the process that we want to be active during freeze out in order for us to be able to shed that heat. Okay, and so in this setup that we've now described for simps, we have these two processes. And if I think about who decouples first, so first we have decoupling of this 3 to 2 annihilation. And then later at some time where we don't really care when, we have the second process decoupling, right? Because we need the second process to be active when freeze out is occurring. So this is the simp mechanism. And I think a natural question you could ask yourself is, what would happen if the order between which process decoupled first was reversed? Okay, so what happens, let's go for a different color here. What if the order was reversed? Okay, and this is going to lead us to elastically decoupling relics to elders. But before we can understand that, we're going to work through cannibals. Okay, so in order to answer this question, let's work through cannibals first. Okay, so what are cannibals? Okay, so let me start discussing here. I'll call this cannibalization or cannibalism. Let's call it cannibalism. So I have fewer letters to write. Okay, so cannibalism, and this is an idea that was put forward by a paper by Carlson, Machakek, and Hall back in 1992. And it was actually based on this paper that we worked through, 20 years later, figuring out idea for getting to the simp. So what is cannibalism? Okay, so let's look back at our 3 to 2 process over here and ask ourselves what would happen if we didn't have these light abundant species to dump our entropy into. Okay, so what would happen if really all we had was just the 3 to 2 process without this second piece, the second knob that we've added into the story? Okay, so let's just write that out. Look at the 3 to 2 process. What if we didn't have light abundant species to dump the entropy into? Okay, so this just could literally be that we don't have an interaction with some type of bath particle, or that there is no bath particle available. Maybe it's a dark sector with a mass gap, many different ways in which this could happen. But what if we don't have a way to dump this entropy? Okay, now if this is the case, then as we mentioned yesterday, there's no reason that this dark sector, these dark particles, need to have the same temperature as the standard model. Okay, so in this case, there's no reason to have the same temperature as the standard model. Okay, so what happens in a sector like this that's undergoing these fast 3 to 2 processes? Okay, well, what's happening is that once dark matter becomes non-relativistic, when the temperature, so once dark matter becomes non-relativistic, when the temperature, and I'm going to give it now a subindex chi, a subindex saying it's the temperature of the dark matter, because it doesn't have to be the same as the temperature of the standard model. When that temperature drops beneath the mass of the dark matter, what's happening is that these 3 to 2 processes are, converting the mass energy of a dark matter particle into some kinetic energy in the final state. And then these are going to sort of continue bumping around and redistributing the energy and transforming that kinetic energy essentially into distributing that kinetic energy back into the bath. And so it's going to heat up the bath. Okay, so these 3 to 2 processes heat up the bath. Okay, and what that does is that raises the temperature. Okay, now let's ask ourselves, how much does it raise the temperature? How much do they heat up? Okay, so to do that, let's remember that we're talking about chi particles that don't talk to anybody else, right? They're only talking to themselves. So chi's in this setup don't talk to anyone else. They don't talk to other particles. And so that means that amongst themselves, the co-moving entropy is conserved, right? Because they're their own secluded sector. So amongst themselves, the co-moving entropy is conserved. Okay, so that means that the entropy in the dark matter, I'll call that S chi, times expansion A cubed equals some constant. Okay, now the entropy of the dark matter, so that in general is the energy density of dark matter plus pressure divided by temperature. This is non-relativistic, so I can just drop that pressure. So what I have is that this is rho chi over T chi. If they're non-relativistic, then rho is just number density times mass. So let's write that out. That's mass times number density. I'm making sure to carry everything with these little labels chi, because things are very different in the standard model sector compared to the dark sector here. Okay, and now I remind you that when we're talking about dark matter that's non-relativistic, and so the number density is exponentially suppressed, right? So let's just write this. So I have here m chi over t chi, and for the number density, I'll plug in over here, m chi, t chi. There's some 2 pi sitting downstairs. It's not important. To the power of 3/2 times, oops, sorry, ran out of space here, times, importantly, the exponent of minus m chi over t chi, right? That's my exponentially suppressed number density with some temperature t chi.
Could I ask a quick question?
Excuse me?
Could I ask a quick question?
Yeah, of course.
Thank you. So since we can't say anything about the relationship between the standard model temperature and the dark sector temperature, could this whole thing be happening during inflation?
So let's first work out what's happening. So you see, I'm already assuming over here. Okay, first it depends, of course, on when inflation is happening. Okay, that's a question that we don't really have a good answer for, right? There's a lot of model dependence on when that's happening. Let's first work on. So what I think is a good idea here, and also to keep in mind, is that over here I'm talking about a number density for dark matter. I'm talking about non-relativistic. So again, you really care about when inflation is happening. So I think that's going to come down to more specifics about inflation. But in a moment when we finish working through cannibals, you'll also see why. Well, first you're going to see what happens to the temperature of the dark sector compared to the standard model. And we're going to see if this is going to lead us to very, very light dark matter, which is very problematic. Okay, so going through cannibals, purely through cannibals without some caveats is somewhat problematic, regardless of where we want to place inflation in the story.
Okay, thank you.
Okay, sure. Okay, so here's our entropy. And I remind you, we said this entropy is constant.
Sorry,
right?
one more question.
Well, the entropy, the co-moving entropy.
One more question.
Is there another question?
Yeah.
Sure.
Yes, sorry, I can't really read your handwriting. It's like m chi over t chi times m chi t chi over something to the power of 3/2. What was that something?
Oh, this factor down here?
Yeah.
Yeah, sorry, it's just a numerical factor. It's not important. It's
Oh,
2 pi.
right.
I don't even think we
Thank you.
bothered writing it in the past. Yeah, yeah. Sorry about that. It's really not important. So you can even just forget that all that's important over here is that we said that my co-moving entropy is conserved, and you see that the mass over temperature is appearing in an exponent. Okay, and so when you work through this, what this means is that conservation of entropy thus implies.
Sorry.
Okay, and you can work
something?
through this. Just all we care is that the temperature of the dark sector scales like 1 over the logarithm of the scale factor, which means that it's 1 over the logarithm of 1 over t. Because I remind you that scale factor goes like 1 over temperature, where this t that's not carrying a little subindex is the temperature of the standard model. Okay?
Sorry, can I ask something?
Yeah, of course.
So we said that this 3-2 process heats up the bath, but I mean, if it is only an interaction among the dark sector, I don't understand how this heats up the bath.
Well, so the 3-2 is pumping heat in. Actually, whether you have in addition also 2-2 self-scatterings or not, I mean, we're talking about strong interactions. So there could also be strong 2-2 self-scatterings, chi-chi to chi-chi. But even just the 3-2 itself, it's heating up the bath because it's pumping the energy. The energy is getting redistributed as these guys hit each other around. Okay, and without understanding anything from that perspective, what we've just worked through together right now is the fact that if I have a secluded sector, you see that that the entropy conservation in that sector tells us that the temperature of that sector is exponentially growing compared to the standard model bath. Okay, so let me just write out that sentence. Okay, what we see over here, what we just arrived at this equation is telling you that the chi temperature is growing exponentially compared to the standard model bath. Okay, we've arrived at this now just from entropy conservation. Okay. Now, if we're in a sector that undergoes this type of so the reason that we call this cannibalizing, okay, we could have written this also earlier, but we call this cannibalizing because you can kind of think of it that the chis are eating themselves through this 3-2 process in order to stay warm. Okay, so that's sort of the origin of the name cannibalism, or undergoing cannibalization because the chis are eating themselves to stay warm. Okay. So we have a sector that is cannibalizing. It's getting warmer and warmer, and we can estimate what is the abundance of the dark matter in a sector of this sort. Okay, so we can also estimate the abundance, and so for that, let's write the following. So let's look at the mass of dark matter times the number density today. Okay, so that's basically rho dark matter today divided by the entropy today. And what I can do is just redshift number density and entropy. They both redshift like temperature cubed. So I'll just redshift them from today back to freeze out. Okay. So here's m chi, n chi at freeze out over s at freeze out. And now we just, instead of writing rho as m times n, we're just going to relate it to entropy. So this will be T at freeze out of the chi sector times entropy of chi at freeze out over S of freeze out. Okay, so I've just substituted rho, writing it in one way, to rho, writing it as temperature times entropy. Okay. And so now let's look at the relic abundance today. Okay, omega chi, where omega chi is just, it's rho chi today divided by the critical value. This is the regular way you've probably seen the abundance of dark matter written throughout the school. So rho dark matter is the mass times the number density. What I'm going to do, mass times number density, and this is of course all today divided by rho critical. And what we're going to do is just take the previous line, Okay, let me call this equation now 3 stars. Okay, I'm just going to plug that in over here. And what we have is T chi freeze out, S chi freeze out divided by rho critical, S naught divided by S freeze out. Okay, I've just carried over from the previous line, and if you plug in all of the numbers, including all the order ones, etc., what you find is 0.6 m chi in EV units over x at freeze out, x of chi at freeze out times x chi freeze out divided by s freeze out. Okay? And so what this equation tells you is that if we have a sector that's undergoing cannibalization and nothing else is happening, then unless we have a huge difference in the entropies between the sectors at freeze out, we have very, very light dark matter. Okay, this is dark matter that's certainly, you know, in the EV range, definitely below the keV scale, definitely sort of in, behaving like warm dark matter, which has its issues. Okay, so we get super light dark matter unless we have huge temperature difference or maybe number of degrees of freedom difference. Okay. So this is cannibal dark matter. Now, how do we go from cannibals to elders? Let's go back to that question that I was asking in the SIMP where we had these two processes, and we asked the question of what happens if we reverse the order. Okay. So we've learned if I turn off one of the processes, the elastic scattering, we have cannibals. Okay. Now let's go from cannibals to elders.
Could I ask a quick question about that last part?
Sure.
Thanks. So it seems like the implication here is that it's somehow problematic to have a large difference in the number of degrees of freedom between the sectors. But why is that something that we couldn't just write a model for?
Oh, it's not a problem to have. I'm giving you what the equation tells you. It doesn't mean that there aren't ways to make this viable. My focus isn't going to be on cannibal dark matter, but rather how we go from cannibals to elders. Okay. This isn't a statement saying that you can't do it. It's I'm trying to point out to you how you, for instance, could get heavier dark matter. If you do have such light dark matter, you run into troubles with structure formation. And this is why a paper, you know, when this paper was put out in the 1990s, originally there was a point in time where, given all sorts of measurements in the power spectrum, people thought it would actually be good to have something that looked and behaved a little bit like warm dark matter. And then another set of measurements came back and said, no, that's not a good idea. And then sort of this, the whole cannibal dark matter sort of sat at rest. So if you look at like the citations for this 1992 paper, it's basically very, very, very small numbers until sort of revived after SIMP came out, sort of mid 2010s.
Okay, thank you.
But yeah, this isn't a statement that you can't make it happen. I'm just pointing out to you what would have to happen. Yeah, but absolutely you could try to model build it. You might once you write down a particular model, you have to check that, you know, everything works out. But it's definitely not something that's impossible. Okay. Okay. So let's move now from cannibals to elders. Okay. So what we just saw is that if we have a bath of particles, okay, so we just saw, that if we have a bath of particles, chi, that undergo these chi to 2 chi's, these 3 to 2 processes, then we have cannibalization. Okay? Now, let's imagine that at some time before this 3 to 2 process freezes out, this bath was at some point in its history in thermal contact with the standard model. Okay? So let's see what happens in this case. So suppose at some time before 3 to 2 freeze out, this bath was in thermal equilibrium with the standard model, and it decoupled at some temperature. Okay, I'll call that decoupling temperature, And at the point that it's decoupling, this is the point where the temperature in the two sectors is the same. So I can also write this, the temperature of the dark matter is at the moment of decoupling is the same as the temperature of the standard model bath. Okay, this is sort of how we define this temperature. Okay, now since after decoupling, we said after decoupling this 3 to 2 process is going to freeze out, and once the sectors have decoupled, then each sector redshifts independently. In each sector, the entropy is separately conserved. Okay. And so we can write that the entropy ratio of entropy of the dark sector at freeze out compared to the standard model at freeze out, this is just the same as the ratio of entropies at the time of decoupling, okay, because they redshift the same. Okay, and so what that means is that if we go back to this equation over here, let me give this equation a name. Okay, so this equation, I think we're up to like 4 stars. Okay, this equation over here, you see I can just replace this factor over here with the ratio at decoupling. Okay, so this equation now becomes that the abundance of dark matter is 0.6 m chi over EV over x of chi at freeze out, s chi decoupling over s decoupling. Okay, and now let's estimate what is the size of this ratio. Okay, ratio of entropies. So this ratio of entropies, s chi decoupling over s decoupling, let's just look what happens over here. Okay, so if we have relativistic, if we're talking about if T decoupling is much larger than m chi, okay, so if the particles are relativistic, then this is, you know, some order 1 number, or maybe more accurately, it's ratios of number of degrees of freedom, which maybe you can make to be large, okay? But what happens if it's non-relativistic? Well, if it's non-relativistic, and you can work out, this entropy ratio is just, you know, it's some numbers here, and it has some m chi over td. I think it's to the 5 over 2 power. That's not important. What is important is that it's exponentially suppressed. Okay, e to the minus m chi over td. Okay, so this is really the important factor. If decoupling is happening when the dark matter is non-relativistic, we have an exponential suppression sitting over here. Okay. Now let's figure out when how we can express this this decoupling temperature. Okay. So when does it decouple? Okay. Well, decoupling happens when the elastic scattering between the two sectors shuts off. Okay. So here's our elastic scattering. Chi, you know, chi photon, for instance, goes to chi photon, stops. Okay, so let's estimate when that happens. So we know how to estimate when processes decouple, right? We take the rate and compare it to Hubble. And the rate for this process, again, if I'm a dark matter particle, then my rate is proportional to whoever I have to meet. So that's the number density of the photons times the strength of this interaction, which is this sigma v for some elastic process. Okay. So this first factor, I remind you, this is coming from the fact that we have to meet a standard model bath particle. Okay. And we just have to compare this to Hubble, which is temperature squared, and we're talking about the moment of decoupling, so it's temperature at decoupling squared over m Planck. Okay. So now let's just shift things around over here. Number density of photons. Photons are relativistic, so they scale like temperature cubed. So what I have here is Td cubed times sigma v elastic goes like Td squared over m Planck. So I cancel T squared and one of those over here. And what we've now found is that sigma v elastic scales like 1 over T decoupling m Planck, or just written another way, I can write this as m chi over Td to get that unitless x variable times 1 over m chi T m Planck, excuse me. Okay. What's important here is that this elastic scattering cross-section is scales with this mass over temperature. Okay. And I remind you that the mass over temperature was what was sitting over here inside our ratio of entropies. And that same ratio of entropy is what was sitting here inside our abundance. Okay? And so what we've essentially arrived at right now is the fact that in the scenario that we're talking about now, where first elastic scattering decouples, and only later does 3 to 2 freeze out, the relic abundance of dark matter is exponentially sensitive to the thermally averaged cross-section of this elastic scattering. Okay? So this is the reason that this type of dark matter is called an elastically decoupling relic, or in short, it's called an elder. Well, let me just give you the references for elders. So this you can find in 2 papers. The first one is by Kuflik, Perlstein, and Tsai. Oh, and also, there was also Ray Laurier. So this was a PRL that is 1512.04545. And they have a longer paper about the phenomenology of elders. Oh, so you can look at it 1706.05381. Okay. So this is elastically decoupling relics, where the relic abundance is exponentially sensitive to the size of that elastic cross-section. And so going back to sort of comparing to the WIMP, to the SIMP. So I remind you that SIMPs we had, right, chi. Let's compare this to the self-scattering that we just, the scattering off of standard model particles. So for SIMPs, right, in SIMPs, this decouples first and this decouples second. And for elders, the elastic scattering decouples first, and the 3 to 2 is what decouples second. Okay. And just to draw what the freeze-up picture looks like over here, because in this case it's very similar to the WIMP and to the SIMP, but still a little bit different because of this cannibalization in the middle. So if we were to look at this number density over S as a function of X, which is the mass over temperature, then very early times we're thermalized with the standard model. Okay, and then at some point at this temperature, at some X decoupling, the elastic scattering is going to shut off, and we are going to undergo cannibalization. And then at some point, the 3 to 2 shuts off, and we're frozen out. Okay, so this is sort of the picture to keep in mind here. Over here, we're thermalized with the standard model. Over here, we undergo cannibalization, and over here, we're frozen out. Okay, and these two points, this is where the chi gamma to chi gamma freezes out. And down here is where chi to chi stops. Okay. So this is a similar but a little bit different picture for freeze out that occurs for elder dark matter because of this intermediate period of cannibalization. And if you go back to thinking about this picture we've drawn over here about these 2 processes and who decouples first and who decouples second, leading to very different types of dark matter candidates, it's really true, and this is sort of true in general when you have different interactions, that if you look at the relative strength between these interactions, then you really flow from different phases within your theory. Okay, so what I mean by this is that, let's say if I try to think about what's the relative size, okay, of my dark matter standard model interactions. Okay, so these are these 2 to 2 scatterings that we're talking about compared to the size of the 3 to 2 self annihilations. Then what really happens is, depending on the relative strengths, you flow from a regime in which you're WIMP-like to a regime in which you're SIMP-like to a regime in which you're an elder. Okay, so in this region over here, we have ordinary WIMPs. So this is the abundance is being controlled by chi annihilating to standard model. In this regime in the middle, we have simp dark matter, and the abundance is being controlled by these 3-2 interactions. And in the regime over here, this is where we have elders, and the relic abundance is really being controlled by these, oops, let me draw that over here, sorry. The relic abundance over here is being controlled by a process that's not changing the number density, very interestingly, okay? So these different mechanisms are really just different phases of a vast parameter space for dark matter, okay? So this is really the phase diagram when comparing the relative strengths of these different interactions, okay? Are there any questions about cannibals, elders, or simps at the mechanism level before we start talking about some models and talking about dark sectors? Okay. So let's start talking about dark sectors. So what we've done so far together is we've developed a few different mechanisms, and we've understood the behavior, which cross sections have to be what size, and what are the relationships between masses and couplings. And so the next thing that we want to do is go from, well, so we've developed several mechanisms. And we've understood their behavior, in terms of the mass and coupling, etc. And the next thing that we want to do once we have mechanisms set in place is understand what are the models that we can write down that admit these behavior, that give us explicit particle theory realizations of these ideas. So these models are theories that realize these mechanisms. Okay? And just in this context, what I mean is, if I think of the WIMP, so supersymmetry, so Susie is really the poster child for the WIMP, for instance, also for co-annihilations, which we didn't really discuss over here. And we already gave as one example, we saw the toy Z3 model for simps yesterday. Okay, but these are just examples of what I mean, a model compared to the mechanisms. And what I hope to show you today is that these different ideas that we're talking about, these different mechanisms are really very generic in theory land. Okay, these mechanisms are generic in theory land. Okay. So I don't want you to be thinking, like I think often people might, that the WIMP is the generic thing, and for 40 years we focused on it because it's the generic thing. That's not the reason that it was focused on. The mechanisms, all these new mechanisms that are coming forward in recent years, these two are generic, and it's just a question of thinking about it properly. Okay, so let's look at a dark sector zoo. So we know we have our beautiful standard model, right? And here's our standard model. And the standard model itself is by no means like a simple theory in the sense that we know that we have a zoo of particles. And they don't just, it's not just some random zoo, they follow a symmetry structure. Right, so we know that we have our SU3 gauge theory, our SU3 color, cross SU3 weak, cross SU2 weak, of course, apologies, cross SU2 weak, cross U1 hypercharge. And you can ask yourself, why couldn't the dark sector similarly have a zoo of particles, perhaps governed itself by new gauge symmetries? And maybe there's also some way for these theories to be interacting with each other. Okay, and so just inspired by the standard model, let's imagine, for instance, that just like we have QCD in the real world, maybe we have a dark version of QCD. So maybe we have some SU3 dark. Okay, and in fact, it turns out that it doesn't even have to be so QCD-like, so standard model-like. We could really be thinking, instead of taking an SU3 dark, this gauge theory over here, we could take it to be an SU NC gauge theory, or an SO NC gauge theory, or even an SP NC gauge theory. Okay, these are just non-abelian strongly coupled gauge theories that sort of behave like a dark version of QCD. And maybe, just like we have our U1 electromagnetism, our preserved symmetry in the standard model, maybe we have some dark version of that, some dark U1 electromagnetism, which itself has a hidden photon that's allowed to kinetically mix with the ordinary photon. Okay, so this piece of the symmetry over here is going to be some kinetically mixed dark photon, and let me call that capital V. Okay, and sometimes, of course, you see this this guy in the literature. Sometimes people call it gamma dark. Okay, gamma with a D. So these theories that we're going to be talking about over here, okay, all of these gauge theories over here, these are just strongly coupled gauge theories. You can kind of think of them as QCD-like theories. QCD-like gauge theories. And in short, I'll just often call them the sort of dark, almost QCD, okay? Dark cousins of QCD.
I have a quick question.
Yeah.
What in this context makes these gauge groups QCD-like?
Well, all I mean over here, you're going to see in a moment, I'm going to draw an analogy to QCD. I just mean that because they're a non-abelian symmetry, it's believed, given that they have a certain number of flavors, that chiral symmetry breaking occurs, and then you end up with mesons. The story in these gauge theories, the low energy spectrum, is very, very similar conceptually to what happens in QCD. But I'm going to draw that analogy in a moment in a very explicit way. Okay. But if you don't like thinking of them as QCD-like theories, these are just the most general gauge group, right? If I was telling you what kind of theories can you write down, you'd probably start the easiest one. That's just what I was just about to say. The easiest one would be just to do a U1, which is fine, and we'll work through that as well. But you can certainly have, just like the standard model, have more complicated non-abelian symmetries. And what I'm just going to show you is that those naturally admit a lot of the types of behaviors that we've been discussing together. Okay?
Yeah, that's great. Thank you.
Okay. So as I said, the easiest thing, sort of the simplest thing, it could be just the dark U1. Okay. So think of this as sort of a dark version of quantum electrodynamics with some dark photon, or some dark this has a dark photon and some dark particles that are charged under it. Okay, so and then I have some my Lagrangian can contain a kinetic mixing, which I'll call epsilon, so minus epsilon over 2, F mu nu field strength, F mu nu prime for the dark sector. Okay, and maybe I have some, so I'll also have some dark version of E, so a dark ED, and this, is the same thing as saying I have some dark fine structure constant, alpha D. And what this effectively gives us is, if I have all sorts of standard model stuff that can talk with a photon, then my photon can kinetically mix through a strength of epsilon into the hidden photon V and go to dark sector particles. Okay, and the strength that's sitting over here is this ED. Okay, so this is sort of the simplest thing, where all I've done is taken a dark version of QED. Okay, just a dark version of electromagnetism. But importantly, what this kinetic mixing does, is it gives us standard model dark matter. It gives them a way to interact. right? A way to communicate, a way to couple to the standard model, okay? So this is an extremely simple dark sector, and this is an extremely simple thing for us to have in any more complicated dark sector as well. So if this is the simplest dark sector, as we said, dark sector could be more complicated. Certainly our standard model itself is not just a photon and particles that are charged under it. So things can be more complicated. So we could have what I'm calling here these QCD-like dark sectors. And again, all I mean by this are this SU, SO, or SP gauge theories, if the word QCD-like is not to your liking, okay? And what's important here is that these theories are very, very rich, okay? And if we have a rich theory, then that gives us a very rich playground for many dark matter mechanisms to emerge, okay? So rich theories give us a rich playground for many dark matter mechanisms and processes to occur, okay? And this is something that you know is true in general, that if we have a given model, you know, once you have a model, you write down every single process that could happen, okay? And depending on the relative size, the relative importance between these processes, which is going to depend on the particular values, okay? So it's going to span different regions in your parameter space. You're going to find out that a different mechanism is going to be controlling the relic abundance, okay? So just like if I thought of these two types of couplings for that we're looking at for Simpson elders, depending on which one was more important, we had regions in parameter space that were WIMP-like or SIMP-like or elders. This is true in any model that you'll write down. You have to write down all of the different processes, figure out in which regions of parameter space is which one playing the dominant role, and that's going to tell you in this model, in this region, this mechanism is what's controlling the abundance, in this region, something else, etc. Okay, so this is really true in general. And so in these QCD-like theories, QCD-like theories have a lot of mesons, okay? So we have a lot of mesons, okay? So, you know, again, similar to what we have in the standard model, you know, so there are going to be dark equivalents to pions, dark equivalent to kaons, dark equivalent to rhos, etc. Okay, so these are all sorts of dark mesons that these theories are going to have. And we're going to be able to do really interesting stuff with this. And in particular, as I'm going to show you, the dark pions, okay, these are just the pseudo-Nambu Goldstone bosons of the theory. These can play the role of dark matter. Was there a question?
No, I don't think so.
Okay. So, so let's see how this happens. Okay. So before going into the 3 to 2, which is probably the most like quirky, not in the physics sense, just in the normal people word sense, process that we've been discussing. Before delving into that, let me just show you, for instance, in these theories, how you get tons of different 2 to 2 processes. Okay. So let's look at a whole bunch of 2 to 2 processes that we could have. Okay. And all the particles I'm going to write now, like if I write down pi or v, these are all dark particles, okay? So one thing I could have is, for instance, I could have pions, okay? Dark pions that are going into dark rhos, okay? In these theories, the mass of the rho is typically supposed to be above the mass of the pions, which are, as the pseudo-Nambu Goldstone bosons, they're the lightest degrees of freedom. And so this gives you a forbidden channel that exists in these theories. We could also have something similar where here all my pions are now going, if I have charged pions, they're going to go to this dark photon. So this would give me just ordinary 2 to 2 annihilations, which is sort of what we call the ordinary WIMP process. We could also have pions going through an S channel to this dark photon, which then mixes to the ordinary photon, which goes to ordinary stuff, standard model. So this again would be just a WIMP process. We could also have scattering of standard model scattering of these pions off of standard model particles through exchange of this dark photon. Okay, so this is an elastic scattering. So this would be something that is relevant for both SIMPs and for elders. And we can also have semi-annihilations. This is something that goes like this. These are semi-annihilations that could happen. Okay, so you see that in these very simple theories, we have already a whole bunch of different processes just from the 2-to-2 perspective that could happen. And depending on the parameters, which one will be more important will determine how the dark matter relic abundance is set. So, and in each case, in each particular theory that you write down, what you go ahead is compute your Lagrangian. Okay, so in each case, you can compute from your Lagrangian. Okay, so your Lagrangian is written in terms of the parameters of your theory now. Okay, no longer some alpha effective, but rather, you know, for instance, alpha dark and the mass of the pion and the decay constant of the pion and the mass of the vector, etc., etc. Okay, so the parameters of your theory, you compute the cross section. Okay, the cross section that you need for the dark matter abundance. Okay, so that means that now your cross section, you write it as some function of the parameters of your theory. Okay, and then what you can do is translate the size of the cross section that we've obtained at the mechanism level that we've developed previously into the parameters. What does it say on the parameters of your theory? Okay, so you translate the cross section. Okay, so cross section, X section is cross section. You translate the cross section we developed previously into what needs to happen for this model, okay? To understand what parameters are needed in your model, okay? So now we're going to do this for our very strange 3-to-2s, okay? And I hope I'm going to show you these are actually very, very not strange at all. Okay, so let's see the 3-to-2 process for SIMPs, okay? So as I was saying, in a way, I feel like 3-to-2 might seem to you to be the most exotic in the sense that it's less familiar compared to 2-to-2. It might seem most exotic, less familiar than 2-to-2s. But we actually have 3-to-2 processes in the standard model itself, okay? That actually have 3-to-2s. Well, we have these processes, let's write it this way. We have it in the standard model. Okay, so let's see how this works. And to do this, let me draw an analogy from QCD. Okay, so here's a reminder of what happens in QCD in the low energy limit. Okay, so QCD, as we all know, QCD is an SU3 gauge theory, right? An SU3 gauge theory. And if I want to talk about how many light flavors we have, it has 3 light flavors. This is the U, the D, and the S. Okay, the up, the down, and the strange. And this theory has an SU3 left cross SU3 right global symmetry. Okay? And what happens is that the theory confines, okay, the theory confines, and chiral symmetry breaking occurs. And what happens is that this SU3 left cross SU3 right global symmetry that we have is now broken down to the SU3 diagonal subgroup, okay? Now, in the standard model itself, these global symmetries are only approximate because the masses of these 3 quarks are not degenerate, okay? But this is, in the standard model, this is an approximate symmetry. So I'll just write that out. the global symmetries are only approximate because the quark masses aren't degenerate. Okay, so these are approximate symmetries of QCD. And this theory has 8 pseudo-number Goldstone bosons. Okay, these are the degrees of freedom that are related to the broken generators. So this theory has 8 pseudo-number Goldstone bosons. And these are the kaons, the pions, and the eta. Okay? And this theory itself, QCD, has 5-point interactions. Okay? The way that this happens is we have 2 kaons annihilating into 3 pions. Okay? And the way that this proceeds in the standard model in QCD is through a topological term in the Lagrangian that's called the Wess-Zumino-Witten term. Okay, so this happens through a topological term in the Lagrangian that's called the Wess-Zumino-Witten term. Okay, and it's named after a set of papers by Wess and Zumino. The first one came out in 1971, and then there are 2 papers by Witten that were put out in 1983 to complement that.
I have a quick question.
Okay. Yeah, of course.
I might just have like a gap in my knowledge here, but I haven't heard the term topological term before in a Lagrangian. What does that mean?
So whether or not this term exists or not, and I highly recommend reading, well, all 3 of these papers are great, but the 2 Witten papers are really exquisitely written. So I think if you read those, you'll get a really good sense. But what it just means is that whether or not this term exists or not has to do with, so now I'm going to say another word that you won't know what it means, but it basically has to do with the coset space of the symmetry breaking pattern in a theory. Okay, so it has to do with the 5th homotopy group. And so just basically based on the gauge group, based on what is your initial global symmetry and what does it break down to after chiral symmetry breaking occurs, depending on the homotopy group of that coset space, that's going to determine whether or not you have this term or not. Okay, so that's the essence over here of topological. And I realize that that's an answer that still can, it's a little bit more of a difficult thing to break down, but for all practical terms, what this just means is that for any of these gauge theories that we're going to be talking about, provided you have, whether it's an SU or SO or SP, as long as you have either 3 flavors or in the SP case, 2 flavors, which is really like 4 wild fermions, this topological term exists. Okay, so the fact that it's topological or not, you can even just forget about it. As long as you have enough flavors, and enough is like literally 2 or 3, this term exists in your Lagrangian. Okay, and it takes on a very particular form that we're going to see together. Okay?
Okay, thank you.
And so in QCD, we have a term in the Lagrangian which couples 5 pseudonumber Goldstone bosons to itself. And in fact, if you were to take that term and calculate the rate, what you'd find is that the rate is just right to be a simp if the mass of the particles involved is of order 100 MeV. Okay? You'd find that it's just right to be a simp if the mass is of order 100 MeV. Okay? This is pretty crazy. And so inspired by this, let's look at what I'm calling these QCD-like theories. Okay, and let me spell out to you exactly what happens over here. Okay? So you can do this for any of the gauge groups. Let me just literally draw the analogy from the SU3 to an SUN. Okay, so let's imagine that we have an SUN dark gauge theory. Okay, with NF flavors. Okay, and I'm going to write down a degenerate mass for them. This degenerate mass, unlike in the standard model, will make sure that my global symmetries are actually exact. Okay, so this is going to stabilize our residual. Stabilize the residual symmetry. So that's part of what's going to make sure that our dark matter is actually stable. Okay. And so if we have this SUN gauge theory with NF flavors, then we're going to have a global symmetry, which is going to be an SUN left cross SUN right. Here's our global symmetry. And then chiral symmetry breaking, that's how I'll write it in short, occurs. And what happens is that this SU cross SU breaks down to the diagonal subcomponents. So it breaks down to SUN diagonal. Okay, and because of this degenerate mass, this is now an exact global symmetry of our low energy theory. And we're going to have some number n pi of pseudo-Nambu-Goldstone bosons. Okay, this is what I'm going to collectively be calling the pions. And these are excellent candidates to be dark matter. And these theories have 5-point interactions. Okay, through this Wess-Zumino-Witten term. And let me show you what it looks like. Okay, it has a very particular form. Here's the Wess-Zumino-Witten Lagrangian. So it looks like 2n, n is my number of colors, over 15 pi squared, f pi to the fifth. F pi is my pion decay constant. Let's just write that out. So this is my pion decay constant. And here is our 5-point interaction. So first I have an epsilon tensor, epsilon mu nu rho sigma. And then I have a trace of a whole bunch of stuff. Okay, I basically have pi, d pi, d pi, d pi, d pi with all sorts of indices here, mu, nu, rho, sigma. Okay, so what we have over here are 5 pions that are contracted in a very particular way. Okay, they're contracted antisymmetrically, some of them with derivatives, some without. But you see it's a very particular 5-point interaction, and it has also a particular coefficient now written in terms of the parameters of the theory, which is the pion decay constant. And this little exercise that we just did now for the SU gauge theory can be done in general. You can do this for also, you can do it for the SO, or for the SU, or for the SP and gauge theories. For the first two cases, in order for this term to exist, you have to have at least 3 flavors. And for this SP case, you just have to have 2 flavors, which are really just 4 wild fermions, okay? So provided you have enough flavors, this topological term, this Wess-Zumino-Witten term exists, and we have 5-point interactions. 5-point interactions give me exactly this 3-to-2 annihilation that we wanted, where now these dark matter are all dark pions. Okay, and so this 3-to-2 interactions, these 5-point interactions or 3-to-2 annihilations are completely generic in QCD-like theories. Okay, there's absolutely nothing exotic about them. This is just a term that almost always exists in QCD-like theories. Okay. And what we can do, as we said, is we take this term that we have, and we can now compute the cross-section, the 3-to-2 cross-section, in terms of the parameters of the theory. Yeah, of course.
I understand that this term induces 4-point interactions, but
this term, no, it uses 5-point interactions.
Sorry,
it's a 5-point
interaction. Yeah, sorry.
Mm-hmm.
But can you give an example in the standard model of a 3-to-2 process that we have measured experimentally? Because
yes, 2 kaons annihilating to 3 pions. It proceeds exactly through this term.
Sure, but this is 2-to-3. I mean 3-to-2.
Yeah, but all we care about is that the interaction, the direct 5-point interaction exists.
Sure.
So you're right. The one that we've measured in the standard model, because of the fact that the masses are not degenerate, our kaons and our pions, which here I'm collectively calling pions in the dark sector.
You also have
they're split in
pion proton and many others, not only pion kaon, but
we have many others, but I'm talking about the ones that are really the pseudo-Nambu-Goldstone bosons, not about the more complicated mesons, but the ones that are really the that are related to the coset space, to the broken generators of the global symmetry.
Yeah.
So what I meant when I'm saying in the standard model, we have 2-to-3 annihilation, the 2 kaons annihilating to 3 pions.
Yeah. Okay, and
but it's proceeding.
And the reverse process is allowed, but it's kinematically suppressed, I guess.
Exactly.
But this wouldn't be.
What's important is that the term exists in the Lagrangian. It's a direct
Okay.
5-point contact interaction term.
Okay, I understand that for that matter, this wouldn't be the case for the dark sector
Well,
that you are considering.
no, so for the dark sector, what I'm showing you here is that this 5-point direct contact term in the Lagrangian generically exists in strongly coupled gauge theories.
Okay, that's good. Thanks.
Okay? The standard model is a little bit more complicated because we don't have the degenerate masses, because there's splitting, but as a story, it's an identical story. But over here you see that in a general dark sector, you just generalize, and it basically holds for any n and for any nf. Okay? Any number of colors and any number of flavors, provided there are enough flavors, which is a very minimal requirement. Okay? So let's see, from this contact term, from this Wess-Omino term that we have in our Lagrangian, which gives us 3 to 2 annihilations, let's now go ahead and compute what is the 3 to 2 cross section. Okay, and this is not a pleasant exercise, and it's one that we did. So let me just give you, I'll give you just the reference where we did this for the first time. Oops, over here, in terms of these pions. So this was a second paper that we had, which was with myself, with Kuflik and Murayama, and with Wolanski, and with Jay Welker. So this was a second PRL. Oops. This was a PRL that was 1411.3727. Okay, so this is work that's called the simplest miracle. Okay, because this is the sort of the simplest realization of this idea. And so let me just show you what happens for these pions. So you take this Lagrangian and you compute a 3 to 2 cross section, and here's what it looks like. Here's my sigma v squared for 3 to 2 in this particular theory with these different gauge groups. So it looks like 5 square root 5 over 2 pi to the 5th, number of colors squared over x freeze out squared, m pi to the 5th over f pi to the 10th, and then some factor, I'll call it t squared over number of pi cubed. Okay, where this last factor over here is some combinatorical factor that depends on the group and on NF. Okay?
I have a quick question.
Of course.
Are you assuming any interactions with the standard model when you did this calculation?
Yeah, so we're going to, so as I said, right now we're focusing on the 3 to 2 side. In this theory, and that's going to be the next thing that we're going to do, you can easily embed within your residual symmetry, you can embed a U1, which is still preserved. And so this gives you automatically a kinetically mixed hidden photon, and it tells you exactly how it couples to the different pions. And then you can compute from that what types of constraints you have. So that is being assumed over here, and that's going to be the next piece of the story that we're going to be talking about. Okay?
Okay, thank you.
Okay, so here is our 3 to 2 cross section. What you see is that now what we've done is we've written out the cross section in terms of the parameters of the theory. So thinking back of the way that we parameterized previously, the cross section is some alpha effective cubed over mass to the 5th. That was just a way for us to parameterize prior to having a particular model. You see that over here, instead of what we do is basically translate. In the old language, you sort of translate this alpha effective that we wrote down to our parameters. And so, for instance, over here, that means that alpha effective is, some number times what's really important in our case, the parameters are m pi over f pi to the 10 over 3 power. Okay, so there's a direct translation between results we've obtained previously to the parameters of this theory. And what this ends up looking like is the following. So here is, now we look at what is the solution to the Boltzmann equation. So now instead of writing what is alpha versus m or something like that, we write down the parameters of the theory, m pi over f pi, as a function of pion mass. And if I draw this in GeV, then you find something that goes like this, okay? And roughly you start hitting sort of strong couplings of order 2 pi when the mass, 2 pi, when the mass of the dark matter is around a GeV, okay? So what you get over here is roughly some range of MEV to GeV, and I'm going to make that more precise in a moment. Okay. Okay. So before we move into talking about how we about the kinetic mixing and how we share a temperature with the standard model, which, as we said, is a very crucial component, just to sort of finish understanding what's the parameter space in terms of the pions, then there's another important thing that we have to take into account. Okay. So, and that is self-scatterings. Okay. Not self-annihilations, but rather self-scatterings. Okay. So if you remember at the beginning of our time together yesterday, one of sort of maybe the second or third thing that I said that we know about dark matter is that it shouldn't too strongly self-scatter with itself, because that distorts dynamics in dark matter halos. Okay, so we have to be careful about this because it distorts dynamics in dark matter halos. But importantly, the reason that we're going to be discussing this here is that you'd expect that if you have theories that have these strong 3-to-2 self interactions, that you'd also have unsuppressed 2-to-2 self scatterings. Okay, so this is a point that needs to be addressed over here. And so from the experimental side, if we look at here, this is what I mean by self scatterings. It's dark matter bumping into each other and sort of shifting things around. From the experimental side, we roughly know that the cross section for self scattering, usually written divided by the mass, should be roughly smaller than around 1 centimeter squared per gram. Okay, and this is what we know from bullet cluster and from halo shapes. And what exactly is this number? Okay, this is like a squiggly line, whether it's 1 or 0.1 or 10, up to an order of magnitude, which changes depending on velocity of different systems. This is sort of the ballpark of how large you should or shouldn't let your self-scattering cross-section go. And there are also some interesting puzzles in this context, which you might have heard about. So one is called core versus cusp, and the other one is called too big to fail. Okay, so core versus cusp is just a statement that if you have collisionless dark matter, it would predict dark matter densities that are very cuspy. The profile should be very sort of have a density that gets very large towards the core, whereas observationally they should be flatter. And too big to fail is just a statement of a mismatch between the Milky Way's brightest stars and its biggest satellites. Okay, so these are whether they're puzzles or not. I don't call them problems. They're certainly not problems. I think if anything, they're puzzles. And it's very possible that these issues are addressed by aspects in astrophysics. Okay, so possibly addressed with pieces of astrophysics that haven't been included so far in simulations, such as baryonic effect. But importantly, what this tells you is that if you have self-scatterings up to around this size, you could also be helping to address these issues. Okay, so but also tells you that if we have self-interactions that are of order a centimeter squared per gram, then you can assist in these in solving these issues. And a centimeter squared per gram, let's just move that sort of to our particle physics units. This is roughly of order, let's say, 100 barn per MeV. Okay, so this is really of order a strong scale interaction. Okay.
I have a quick question.
Mm-hmm.
Could you say a little bit more about how a strong scale interaction could fix the too big to fail problem or help with it? Puzzle, not problem.
Yeah, I don't want to go into these into these puzzles too much. That's definitely, I could have actually not even addressed the puzzle and just said, well, let me make sure my cross section doesn't go too large. But it's really it's the same statement. It's the fact that I distort dark matter halos. I'm sort of changing the way that things are distributed. Okay. If you want, we could discuss this maybe a little bit more if we end up having a discussion session tomorrow. But I don't want to delve into these puzzles because they're really not the main focal part, and there's some complexities that have to do with them. But let me give you there's a great review if you want to read more about this. There's a great review by Sean Tulin and Haibo Yu. So it's 1705.02358. Okay, so these are really people who've been doing a lot about really working out the details of what exactly are the details of the problems, when do they really appear, when do they not appear, how do things depend on velocity, and what are then the statements related to related or not related to self-scattering. So I think that would be a good place to do some in-depth reading about it. Okay.
Okay, thank you.
Okay. So let me sure. So let me take all of this conversation and sort of move back to why I'm even mentioning this, because as I said, when we're talking about our strongly interactive massive particles, then you just expect that if you have some theory that has strong 3 to 2 interactions, you'd also generically have strong 2 to 2 self-scatterings. Okay. You'd also generically have strong 2 to 2 self-scatterings. Okay. And so this is, you can think of this on the one hand as a constraint on your theory, and the other hand as a potential signal, because you're going to get a contribution that's exactly of the right order to be addressing these issues. Okay, so it's this is both a constraint plus a possible signal. Okay, and so what this means, if we look back at our parameter space, okay, so if I look over here at the mass of my pion compared to m pi over f pi, the parameters of my theory, then we saw that this is my solution to my Boltzmann equation. Okay, so this is the solution to the Boltzmann equation. So this is what's giving me the right relic density of dark matter. And what you have now in addition is that along this solution to the Boltzmann equation, so for every m, I have an m over f that's giving me the right abundance. And so along this solution, you can plot, or you can compute what is my self-scattering. Okay, so let me write that down here, and then we're going to draw what it looks like. So here's my Lagrangian, for instance, in our pion story. The Lagrangian definitely has 4-point interactions between pions. So we have something like m pi squared 12 f pi squared trace of these pi to the 4th 4 pion matrices. And then we also have 1 over 6 f pi squared trace of things like pi squared d pi minus pi d pi d pi. Okay, so things are contracted in various ways. And you take all of this and you compute to yourself, here's my self-scattering cross-section. And it has this particular form, m pi squared over, the numbers aren't really important. I just want to show you that in principle, you take your Lagrangian, you compute something from it, and then you assess what does this tell me about my parameter space. Okay. So here's 32 pi squared f pi to the 4th times, again, some combinatorical factor. I'll call that a squared over n pi squared. And again, this is a combinatorical factor over here. Combinatorical factor that, again, depends on your choice of gauge group and number of flavors. Okay. And so you see that what it depends on is exactly, the mass and the decay constant, okay? And so along the solution to the Boltzmann equation, if I now require that this sigma is smaller than a centimeter squared per gram, this also gives me some restriction on my parameter space, and it looks something like that. So here's, let's say, my sigma. This is my curve along that solution. And what I end up with is combined, on the one hand, I can't allow m pi over f pi to be too large, right? And that's going to give me sort of an upper bound at around the GeV on my mass. And from the same side, once I require my sigma, my cross section, which I've drawn here in pink, to be smaller than some value, then that's going to set, some other unit. Okay, it's going to tell me that sigma has to be smaller than some number, and so that's going to give me some lower bound on my mass. And this range over here usually points us to order hundreds of MeVs for the dark matter mass. Okay, and so the theories, these pion realizations of simp dark matter, much like the mechanism level was telling us itself, really point us to dark matter masses that are between the MeV and the GeV mass scale, typically of order hundreds of MeV. Okay, so simp dark matter masses really sort of between the MeV and the GeV mass scales. Okay. So far, we've only talked about what happens to the pions themselves. And as was pointed out, of course, very, very crucial to this whole story was the fact that we had to also be able to talk to the standard model. Okay, and so, oops, let me give you. I'll give you a couple of references for different. Actually, before giving you those references, let me just also point out that in the context of 3 to 2 in these QCD-like theories, there's also cool ways to do stuff with glue balls. So, for instance, if you wanted to do 3 to 2 through dark glue balls, there are a few. So one way is, of course, this first paper, which is Carlson, Manchakek, and Hall, this 1992 paper, the cannibalization paper. Then there's a Sony, oops, there's a paper by Sony and by Zhang from 2016 that looks at 3 to 2 glue balls. And there's also a paper by Forstall et al. From 2017. So these are definitely the 3 to 2 pions are not the only way to go. You could also be using glue balls, but just to sort of show you how much richness there really is in terms of the options. And how do you mediate the interactions? Again, could be many different ways. One way, which we're going to look into in detail right now, is to use the kinetically mixed dark photon. So let me just give you the reference for that. So that's work that we did with Kuflik and Murayama. That's 1512.07917. So this is going to be the dark photon, and using an axion was a paper with Kuflik and McGee and Murayama and Schutz, and that's 1806.10139. So this one is the axion portal, and this one is the photon portal, which we're going to talk about now. Okay. So it's not just a question of how do we interact with, how do we interact with the ordinary matter. It's also how easy is it to do, and of course also what are the predictions that that these ideas give us. So, so the dark sectors that we've just built now with these pions are also extremely predictive. Okay, so let me show you what I mean by that. So, for instance, let's stay with our QCD-like theories, and let's do times the dark electromagnetism. Okay. And as I said, and you can look at the details in our dark photon portal paper, which is called SIM spectroscopy, the dark photon can naturally be embedded into the global symmetry that we have remained. So this is just a natural, there's nothing new that you really have to do to the story. But let me show you what this looks like. So here's my regular photon. And it's going to kinetically mix into the dark photon that's sitting over here. And if you ask yourself, well, what is the size of this epsilon as a function of parameters such that, I'm in different regimes of different theories. So let's draw that over here. So here is, let's say what I'm going to do here is I'm going to fix, let's fix the gauge group. Okay, it looks very similar for all gauge groups. And let's also fix the mass of the dark matter. Okay. And for instance, look, as a function of the dark photon mass and epsilon, what we have, okay? And so we have very interesting stuff. So there's one curve over here, which is the curve of thermalization. Okay, so this down here is where thermalization is happening. This is essentially the curve along which we have elder dark matter. We have some curve that looks like this. It dips down because there's a resonant contribution. This is the curve where ordinary 2 to 2 annihilations happen. So this is the curve of the WIMP, and it digs down over here at this point over here is exactly twice the dark matter mass. Okay, so of order a few hundred MeV. And so just in this parameter space, you see over here, I could be in a WIMP-like regime, I could be in an elder regime, and in between is where I have SIMPs. Okay, and just to add on to that, if I look at dark matter that's beneath this resonant contribution, this is the regions where semi-annihilations can contribute. Okay. And so again, different regions of the parameter space will give us different realizations for dark matter mechanisms, okay? We can be a WIMP, we could be a SIMP, we could be an elder, we could have semi-annihilations. And just depending on where we are, we'll get something that'll be very different. And so this parameter space has many constraints that already exist on it. So we have constraints on the parameter space. And these come from a whole bunch of different experiments. They come from high energy and low energy colliders. They come from beam dump and fixed target experiments. Beam dump and fixed target. Well, let's write this out a little bit differently. Okay, so we have, oops, let me do this a little bit differently. Okay, we have all sorts of different constraints on this parameter space from the high energy and low energy colliders. And we also have many different future probes. Okay, so if I just look at this, let me just show you, this is gonna go pretty wild over here. Let me just redraw this over here. So here's epsilon versus MV. Okay, and we have this, right? We have this dip over here, whoop, and we have this curve down here. Okay, so roughly speaking, what you have in terms of existing constraints, there's it kind of goes, let's say something, okay, this is, if you want to look at the exact, of course you should open up a paper. This is just sort of to give you a taste. The constraints are between roughly 10 to the minus 3, 10 to the minus 3 to 10 to the minus 2 over, you know, most of the parameter space, okay? And all the different types of future probes that come from all sorts of different machines, okay? They're going to come from future high energy and low energy colliders, and from beam dump and fixed target experiments, and from direct detection experiments, and lots of different things. These constraints are sort of, you know, expected to do orders of magnitude. You know, where they're going to do better depends on, I'm just sort of randomly drawing all sorts of curves here. Each one of these different types of experiments is going to cover huge portions of this parameter space and do a great job at probing, maybe constraining, hopefully actually detecting this type of mediator, this type of kinetically mixed hidden photon. Okay, so over very broad ranges of dark photon masses, we have many different ways to probe this parameter space. But the thing that I think is actually most exciting, if I'm thinking of future probes, is that we can even go further. Okay, we can go even further. We can hope to perform spectroscopy of our dark sector. So let me just explain what I mean by this, and this is going to be the last thing that we're going to be covering together. So again, let me sort of draw an analogy from QCD. Okay. Draw analogy from QCD. Okay. So how do we know the beautiful, messy resonance structure of QCD? Okay, how do we know the beautiful resonance structure of QCD? The answer is that we smash electrons, positrons on each other, and they go to all sorts of stuff that hadronizes. Okay, so we have, we smash E plus E minus on each other. It goes to all sorts of stuff. And basically by scanning the center of mass energy at which we smash stuff at each other, we scan the stuff, okay? So here's electron, positron hitting each other and going to all sorts of stuff, okay? And the way that we really get the entire structure is that we scan the center of mass energy, square root of S, and by doing that, we scan the stuff that we see at the end, okay? And this is the way, so we smash this, as we said, as center of mass energy. And this is exactly the way that we get this beautiful picture that I'm going to draw here, not so beautifully, but I'm sure you've all seen in the past, as a function of square root S, let's say in GeV units. We have some cross-section, and this is how we see, here's our rho, and our omega, and our phi, and our j psi, and psi 2s, and upsilon, and ta. Okay, so here's rho, omega, phi, j psi, psi 2s, etc. Okay, the whole structure, this is how we've seen it. Okay? Now you can ask yourself, how could I hope to see something similar if instead of the ability to scan my center of mass energy, I had a fixed energy machine. Okay? So if I wanted to do this, so how can we do this at a fixed energy machine? The answer is, let's tag on a photon. Okay, here's, whoop. Let's look at monophoton events. Because in this monophoton event, the energy of that photon is in one-to-one correspondence with the invariant mass of the system that it's recoiling against. Okay, so the answer is monophotons. Okay, so we add the photon. And it's exactly a tracer for the system that it recoils against. Okay, so here, let's just draw that exact same picture, but now let me just draw it differently. Here's my E plus E minus, goes to a photon, and here's my stuff. Okay? And all I know is the energy of that photon, which goes like square root S over 2, 1 minus the mass of the invariant system on the other side over S. Okay? And so the stuff that's coming out doesn't have to be stuff that's visible to me at all. It doesn't have to be hadrons of the standard model. It could be dark stuff too, okay? Because if we can tag that monophoton, if we look at monophoton events, we're actually going to be able to understand the resonance structure of any stuff, including dark stuff, that it scatters against, okay? So we can do this exact thing for dark stuff too. Okay, and just to show you what this looks like. So, for instance, at a low energy machine like Bell 2. So this is, for instance, at Bell 2, you could hope to see something like this. So you look at, let's say, the energy of these monophotons compared to, let's say, you look at how many events per 100 MeV. And you have some spectrum where you're able to see one resonance, a second resonance, a third resonance, etc. Okay, so here will be like some tower of dark resonances. Let me just call those rho and enumerate them. Okay, which you should be able to see at low energy machines such as Bell 2. Okay, so this is the type of spectrum that you'd expect to be able to see for a SIMP like dark sector. Okay. And so this would be easily visible at a machine like Bell 2. Okay.
I have a quick question.
What's that?
I have a quick question, if that's okay.
Mm-hmm.
So why are we assuming that our dark sector is only coupling to the standard model through that dark U1 and not the non-abelian gauge group?
So in this particular case, what I've actually assumed over here. So I recommend reading this second. Let me just point out which reference it is that contains both the spectroscopy. So this reference over here, this one over here. Okay. This one will show you how actually this U1, this dark U1, is a subgroup. It's itself embedded inside the global symmetry. Okay. So in this case, I'm not actually really doing a QCD times a dark U1. It's really that the U1, the gauged U1, is actually a component inside the global symmetry structure. So I start off with, let's say, an SU gauge theory, and I have an SUN cross SUN global symmetry that then breaks to a diagonal component. And inside that SUN diagonal is a gauged U1. Okay, so you naturally don't have to add actually anything in addition. It's actually something you could easily just embed completely inside your initial theory. But you certainly don't have to have, so actually the dark U1 that I'm talking about here is really actually sitting inside it's a gauge component of the global symmetry in the QCD-like theory, okay? But in terms of a gauge symmetry, it's like an additional gauge component because you're gauging part of the global symmetry. But it's by no means the only way that one can do it. You can do it with accent portals and other portals as well. Not all the portals have been worked out in the literature. Because this is sort of a rapidly evolving field, but the one that's sort of been most studied is certainly the dark U1.
Okay, thank you.
Sure. Any other questions? Okay, so this is actually all I wanted to share with you guys today. So just sort of to summarize what we learned together. Hopefully I've convinced you, you know, we've seen that simps are awesome, cannibals are awesome, elders are awesome. And importantly, these things are generic. Just because they're new ideas doesn't mean that they are actually exotic in any ways. And I think most of all, I hope that you take away from what we're discussing not to be an expert on simps or an expert on elders or an expert on cannibals, which I of course hope that you will be too, but really to take away the different tricks and methods and to keep an open mind when thinking about processes, not to take things that have been told to you, you know, oh, nobody thinks about it for reason ABC. Just really think for yourself. Is there something here that hasn't been done? Is there a good reason why it hasn't been done? Can it work? Hopefully I've given you tools to be able to understand if it works or not, sort of at a quick pace, and to understand if it works, what type of mass scales and interactions it points to. As I said, you know, we came up with simps on the beach, and I hope that all of you sitting there in the French Alps, maybe one day when you're having a stroll, you guys together come up with the next amazing idea, or people sitting and listening somewhere else around the globe in similar pretty settings. Hopefully you guys will come up with next amazing dark matter candidate. And that's it. I'll thank you guys for your time.
Thank you very much. One question here.
Yeah, you mentioned yesterday that you would show us your best attempt at this crocodile diagram, and I'm interested to see it.
Nice. Okay, absolutely. Yeah, good point. I realized at the very end, excellent question, because I forgot to show that to you. Okay, so my closest attempt at a crocodile was actually when we were working through the Axion portal. Okay, and here's what the diagram looked like. It's a beautiful diagram. Okay, so here's my 5-point pion interaction. Okay. Okay, so these are all pions. Pion, 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 pion. This is the interaction that comes from the West Zomino-Witten interaction. Okay. Now let me just close this loop over here. Okay, and shoot out an axion. Okay. And the axion has to also couple to standard model. So the axion is going to couple to electrons. Here they are, my electrons. For the sake of having a pretty diagram, we're going to emit some photons over here as well. And the problem, so this was actually the diagram, okay, and then my collaborators who know that they got so excited, and then like we added, here's like an eye and, you know, legs. Those aren't part of the real Feynman diagram. The problem with this thing, it would have worked beautifully, except in our theory, this little vertex over here, this one equals 0. And so I couldn't write this crocodile diagram down. It was very, very sad. There was like half an hour of extreme excitement and then, you know, epic failure. So, yeah. But I definitely repeat, if anybody ever comes up with a crocodile diagram that's legitimate, that fits into your paper, I'll be eternally grateful. And please drop me a line, because I'd love to see that when it comes out on the archive.
Okay, thanks. Challenge accepted, I guess, yes. Thank you very much again, and see you soon.
Thanks, everyone.